Hello, and welcome to the Cedille cast, a series of videos on programming and proving in Cedille, which is a new dependently typed programming language with some rather exotic features. So the intended audience for these videos are people who are already familiar with Agda, Idris, or Coq, other dependently typed programming languages, and who are interested in seeing how to do some programming in a very different style of type theory. So in this first video, I'll be exploring one of the ways in which Cedille is very different from these other languages. Namely, in Cedille, we do not have primitive inductive data types. Cedille is not based on the calculus of inductive constructions. Instead, in Cedille, it is actually possible to derive induction for impredicative encodings of data types. So essentially, we have a type theory where if you start with impredicative calculus of constructions and add a couple of somewhat simple typing constructs into the theory, you come up with what we call the calculus of dependent lambda eliminations, in which it is possible to prove induction for lambda encoded data types. So in this first video and the one that follows it, we'll be exploring this theory a little bit by showing how to derive induction for Church encoded natural numbers. As a refresher, Church encoded natural numbers sort of look like the following. I will say nat as type has kind star and is equal to, for all x, give me an x and an x to x function, and I'll return an x. So essentially, natural numbers are defined in Cedille, just like in the calculus of constructions, as their iterators, where you provide the thing to do in the base case and a function to handle the step case, and a natural number will then apply that function n times on the base case to produce a result. So in this first video, we'll be showing how a failed attempt to derive induction just in the theory of the calculus of constructions, because this will be will help to illustrate the reason that Cedille adds some of these new typing constructs. And along the way, we'll also learn how to write some small Cedille programs and enter some of these strange Unicode characters. So for example, in the definition that I've just written, the left-facing triangle represents, indicates check this definition against this type, and it is entered with \f. The base kind star, representing the type, the kind of types which can classify terms, is input with \s. The for all quantification, which for now you can think of as being the quantifier for types. We'll later see that that's not exactly correct, but for now, for all, which introduces quantifiers over types within types, can be entered with \a. And then the arrow can be entered with \r. So what I just did there was entered, once I have my definition, I type Alt-S, and the Emacs mode will type check my Cedille program. And if everything goes okay, then I will get some nice syntax highlighting for the thing I've just written. So note that in general, the format for definitions like this is name, the classifier, and then the body. And in particular, it's important to have this extra period at the end. Otherwise, syntax, the parsing will fail, and you'll get somewhat unhelpful message parsing error. So make sure to put that full stop at the end of the definition. Okay, well, we defined natural numbers in terms of their iterators. Now let's define some terms which have type nat. First, we can define 0. And here, to introduce type quantification at the term level, we have a capital lambda, which you can think of as being the explicit abstraction for types. Here I'm going to introduce my variable x. Then little lambda for introducing my term. Actually, I will call this base for the base case, step for the step case, and then for 0, what I want to do is return the base case immediately, because I'm applying, essentially, what the essence of 0 is applying step 0 times to a base case, which just looks like base. For successor, I have, which is a function taking nats to nats, the definition looks like the following. I introduce my in, and now I introduce my x, my base case, my step case, and here what I do is invoke the step case on running in on the base and step case. So here, what I do is I run my computation n times, run step n times on base, and then because this is a successor, I will run step one more time on the resulting computation. So before proceeding, it's worth taking a look at one very useful feature that the Emacs mode for Cedille has, which is a structured navigation mode. If I press meta S and enter navi mode, and then I bring my cursor over to the beginning of some part of the text, say over this variable, and I press P, I will highlight the smallest node of the abstract syntax tree that I'm in. And if I press P again, I will step to its parent. From here, I can press F to move forward in the abstract syntax tree, to step in, and then move forward. So that's nice. I have a little way to navigate the syntax tree in a structured way. But there's more to it. If I have a node highlighted and I press I, I'll bring up the inspect buffer. This tells me what kind of node in the tree it is. Here it's an application. What the expected type of the context provided. Here it's x. And the synthesized type of the expression that I've highlighted, x. And then I can see that this variable has this type, and that this application, in, is applied to base, which then requires an x to x function before it produces an x, which is exactly what x has. So here it's very simple and probably doesn't require too much thought, but in more complex programs it can be very nice to be able to zoom into a particular sub-expression and find out what the type of the expression is, and see the types of the sub-expressions as well. Aside from the inspect buffer, there's also a context buffer, so I can actually see, again, if I'm digging down into a definition, I can see what terms are in context, as well as the types. Okay, well with this, I could define I can give some simple definitions, like 1 is equal to successor 0, 2 is equal to successor 1, etc. I can also define some operations on my natural numbers. So again, sorry if I'm moving quickly, /f to check add against a type. Here, type of add is going to be a function that takes 2 natural numbers and returns 1. There's sum in particular. And the way I will calculate it is the usual way with church encoded numbers, is I will run in with a base case of m and a step case. So here, if I want to begin working on the slightly more complicated part of the definition, I can type /h for a hole, which is an incomplete part of the program. And then if I press R, if I press meta S and I've type checked my program with a hole, and I press R, I'll jump immediately to the first error here, which is this hole. So now I can see that this incomplete program has this expected type. So I can introduce it with and if I want to test that this is totally normal, I can press Control-I in to normalize an expression, and I'll say I want to normalize add 1, 2. Yes, and now I get the expected result, which this may not be immediately obvious, but after abstracting over the base and step, I apply the step function 3 times to the base case, which is exactly what I would expect from 3. Control-I in, normalize 3, right? Add 1, 2 looks exactly like 3. So now we've written a small-ish first program for church-encoded natural numbers. Great. Let's start trying to prove induction for them. So to start with, let's give a definition, a type signature at least, for induction, the property that we'd want to prove. Oops. Induction on nats is defined as follows. For all properties P over nats, types essentially indexed by natural numbers, if P holds for 0, and well, now's a good time. So I said before that the for all introduces quantification over types. Again, this is not strictly speaking the complete story. You can use the for all to introduce terms, but this is quantification over erased terms, which is one of the features that Cedille adds, which isn't relevant to this first video. So for now, I'll simplify the story. Apologies. I can type, oh yeah, there it is. If I type right \p, I can introduce a pi, which for now you can think of being as quantification over terms. Or another way to think about it is just pi is the dependent, the abstractor for the dependent function. So here, pi. So another way of saying is for all m nat, if p holds for m, then we expect that p holds for successor m. So essentially, if p holds for my base case, and if p holds for a prior case, I can prove that it holds for the next case, then what I hope to be able to prove is that for all n nat, p then holds. If p and n holds for 0, and successors of numbers for which it holds, then it holds for all numbers. Great, that's my type signature. How do I go about proving it? Well, it's not clear immediately how to go about proving this from the start, but maybe we want to try our hand at something simpler. This maybe seems a little bit silly, but what if instead of trying to prove induction for natural numbers, we just tried to prove that a couple of natural numbers satisfy the property of induction? Well, what do I mean by that? Instead of quantifying over all numbers n, what if I say what it means for just a particular natural number to have to be inductive? Let's define that as follows. inat is a property over natural numbers. By the way, just FYI, for your information, if you are following along, lambdas at the type level, for which this is right here, require type annotations. This at some point will probably change in Cedille, but for the time being, if you write a lambda abstraction at the type level, you must provide a type annotation. Whereas, of course, as we've seen already, lambda abstractions at the term level do not necessarily require one. So here, the only difference is that instead of quantifying over all natural numbers, we're saying that this is a property about particular natural numbers, that given a property P that we want to prove, and based on a step case, that, oh, sorry, I'm missing the last important component, that the property P holds over the particular n. So why is this useful? Well, it turns out that 0 is such an inductive nat. Right? So what I need to show is that for all p, given a p and a base case and a step case, I want to show that p holds for 0. So, sorry, again, if I'm moving too quickly, I can press I to bring up the inspect buffer. Well, let's slow this down entirely. After writing all that, I can press meta S to check the file. I can press R to jump to the first error, which here I don't care about because I'm still in the middle of proving this side case for induction on particular natural numbers. But if I press R again, I'll move to the hole that I do actually care about, where I want to prove p holds for 0. I can press I to see the expected type, and press C to take a look at my local context. Here, the expected, I have something in my context already that will give me exactly the expected type, which is base. So this type checks. And I can then try to show, say, I1, that 1 is inductive. My step case requires the number, as a much as you'd expect in a dependently typed programming language. The first argument is simply a means for the type checker to know what the type of the second argument ought to be. So if I provide 0, suddenly my p of n, 0 gets substituted into this type expression, so that now, once I say n is 0, I know that I must provide p of 0, which I again have in the base case. Now something somewhat familiar in the structure should be becoming apparent. If I skip over 2, just to shorten this, step 2, step 1, step 0 base. What I'm starting to see is that the proof of induction for each of these, the proof of induction for each of these numbers looks a lot like the church numeral themselves. Here, to show that 3 is inductive, I apply a step case 3 times to a base case. To show that 1 is inductive, I apply a step case 1 time to the base case. So maybe the shape of the induction, the shape of the derivation of induction would look something similar. question is, how can we generalize this? What we're sort of seeing here is that what we want is that there is some natural number, some particular natural number, 3, for which the property that we're trying to hold can be shown. And we can actually replace the definitions of inductiveness for 0, 1, and 3 with a schema that looks which each 3 of them can share that looks very similar. So to start, to see what I mean concretely, let's assume instead of adding some of the more exotic type features that Cedille has, what if we just added a plain old dependent pair? Cedille, if you have the standard library already, you can at this point type in import sigma. And this is actually just a library, also given as a Lambda encoding for which induction has been proved. But for the sake of argument, let's pretend that that we added to the calculus of constructions a simple inductive pair type, sigma. What we could see is that we could factor out the commonality, the common structure of these 3 definitions. And by that I mean, let's take 0 and instead say, let's apply 0 to compute a dependent pair. Sorry. So here what I'm saying is that I'm going to be using 0 to compute a pair, the first element of which is a natural number. The second element is a proof that the property that we're interested in, P, holds for the natural number. And in our base case, we will provide base, and our step case, we're providing pairs here, so it's not as simple as that. But as our base case, we will provide make sigma 0 base. And as our step case, we'll take our proof and produce a proof of the successor case. So now, of course, this isn't exactly what we want because we actually just want to return the proof at the end and not the pair of the number with its proof. So this we can factor out in a let statement. So in Cedille, let statement has the following syntax: square brackets with the definition. You can provide an optional type signature if you want, but in this case we don't need it. Well, actually, let's give it anyway. Our proof is a pair whose first element is a natural number, and second element is a proof that the property P holds for that number. And it is given as 0 applied to 2 arguments. We'll leave that blank for now. And then what we want to return ultimately from our function is the second projection of our proof. So right now, Cedille cannot see that the first projection of our proof is 0, but once we finish our definition, this will be obvious. So in our first case, we need to produce a pair, so let's give it make sigma 0 base. Cedille's happy with that. Next, we need to assume some proof P of x holds for a natural number and provide a proof. Here, this proof is for the previous case, and what we want to do is prove the step case. So this looks like, well, it's a little bit easier if we factor this into a let definition as well. So we'll say let in prime be equal to projection 1 of proof prime in the following. definition. Make sigma successor n prime and step n prime projection 2 of the previous proof. And now Cedille is very happy with this definition. Because it's obvious to see that projection 1 of the proof is equal to 0. And if that's not, I mean, it's obvious to Cedille. If that's not perhaps as obvious to humans instead of machines, then we could say, you know, let's 0 prime be equal to projection 1 of our proof. And then again, ask Cedille to normalize this expression, control I n, and you can see that Cedille was able indeed to calculate, to normalize that the first element of this pair is indeed 0, lambda base, lambda step base. So this possibly seems like an overly complicated way to prove that 0 was inductive, essentially, especially because we already had the very proof that we needed as an assumption. So to make it clear what we bought in doing this, what we bought is some generality. Sorry, apparently Emacs does not want to respect my indentation. Here, instead of 0, we can make this 1, and what are we unhappy? Yes. We can make this 1, and everything checks out okay. Again with the indentation. And again, we can take the same body, the same schema, and replace the number we had before, 1, with 3, and this also type checks. So it seems like what we would sort of hope would be the case is that for any n, that we could just compute the same proof and get a proof that p holds for n. Unfortunately, this does not work out the way we expected, and to see why, let's naively take our code and copy and paste it into the body of inductive NAT. So first, we want to introduce our property. We want to bring these into scope, our property, our base case, our step case, and the number we want to prove the property for n. Don't need, actually we'll keep that around. But instead of running, you know, this piece of code on 0, we want to run it on n. And we want to compute an n prime. Right? Unfortunately, even though this same approach worked for concrete values, 0, 1, 3, because we can count, this does not work in the general case. And to see why, let's take a look. So again, we're getting the error that it's not obvious that the projection 1 of proof is equal to n, even though our pair proof was formed by iterating n times a pair producer where the first element is 0 in the first case, and the successor element is successor n in the second case. If we ask Cedille, well, you know, what is it that the first projection of proof looks like? We get this somewhat unwieldy definition, but essentially at a high level what we're seeing here is that n is applied to one argument and another argument. This is not a redex, it's a variable headed application, which means it is in normal form, and even though we expect that this should that if n is a natural number, then that this would always compute to a pair. This right here would always compute to a pair, where the first projection is n itself, and then invoking this first projector. This is the lambda term that, when fed into a pair, gives you the first projection. This first projector would take the first projection of n of the pair computed by n, and that this would be n. But this is not immediately obvious from beta reduction, and unfortunately, type checking fails. So that concludes the scope of the first video. We've gotten this far, and we have seen that a simple approach to improving induction, of course, will not work in calculus of constructions. In the next video, we will show some of the new typing constructs that Cedille introduces: dependent intersection, untyped equality, and of course impredicative quantification, which we have been using but haven't really made too much note of. How these three things come together to allow us to prove induction for our church-encoded natural numbers. Thanks for watching, and hope to see you in the next video.